Hello, welcome to the presentation of my algorithms course homework 4. In this homework, I will solve problems related to randomized algorithm and their running time analysis. So now let's start with a basic practice question on randomized algorithm. Okay, so here, give me a question. It asks me to find in a given array of integers, finding the median of the array, which is the middle element when the array is sorted. And it also wants me to analyze its expected time complexity. Okay, so now let me just stop the video here. I will solve the problem according to this information and I will come back with the solution. Okay, so I found a solution for this problem. As you can see, I asked for ChatGPT if it's correct or not, and it corrected my code like this, as you can see, and my output is correct for the provided input. So now I'm going to show you how I did this. Okay, so here we can see it on the IDE in PyCharm. So firstly, we need to import random because we are working with a randomized algorithm and we want some random numbers created each time. So we're going to use the random model of Python. So the function's name is actually median finder, but it actually works exactly like the quick select, as you know. Let me show you that here, as it showed me here. It gave me a hint here, so I used actually a quick select function here. So firstly, we check if the length, which is the size of the array, is smaller than 1 or not. If it is, we don't need to, move on the process, because there is only one element and we're going to return that one element. So then we have a random index number. This is the index of the array. So we are creating this by random.randint in the interval of 0 and length of the array -1, which is we are creating a random integer number from 0 to the last index number of the array. In here we have a pivot value. We are creating our pivot value, which is randomly created because this I number is randomly created, so our pivot should be randomly created too. Then we are partitioning our array into left and right arrays, and here is a pivot, which is actually the pivot value in the middle. Not in the middle, but it's just the pivot value. So for the left here, we are looking for the elements smaller than pivot value, and in the right we are looking for the elements greater than pivot value. This is how exactly a quick select algorithm should work. And then we have some if statements here. First, we are check if the length of the left is equal to k-1. If it is, we are returning the pivot value. Why? Because this means that so we are working actually a quick select function, but we're looking for only median values. So we're going to use the median value, which is in this case, as you can see, 4. So the length left equals to k-1. This means that the left function, the left partition, is actually one point left side of the pivot number, because let's say we have an array of, as you can see here, we have an array of 7 elements, and let's say our pivot is 1. Then we can say that the k number here is 4 and the left array is 3 here. So if it is, we are returning the pivot value. Then if the the size of the left array is greater than k minus 1, we should check for the left array. So here, if the size of the left array is greater than k minus 1, which means that we are not actually working on the middle. So we have to call our median finder for the left array with the same parameter k, which is actually the median value of the array. And in the other elif statement, it checks whether the size of the left array is smaller than k minus 1. So if it is, we have to move on to the right array, because the thing we should look for is in the right array, and we are calling this with k minus len left minus 1. So this is basically how our algorithm works. So we have an array of 3, 5, 6, 1, 2, 9, and 14, and the array size here is 7. And the mid value of this array should be 4 here. As you can see, it should be 4. And then we create a med value which is uses this median finder function, like here. As you can see, let's run our code again. So it correctly prints out 5. That's correct, because when we sort the array, we can see that 1, 2, 3, 5, 6, 9, 14, and we can see that 5 is actually the value in the middle of the array. When we sort the array, we can see that. So I added 2 numbers here, more 56 and 12. So when we run this code, it gives us the correct answer, which is 6 here, which is correct, because let's sort the array 1, 2, 3, 5, 6, 9, 12, 14, and 56. So we can see that this 6 is actually the value in the middle, which is the median value. So our approach is correct. Okay, now I will move on to the running time problem of a randomized algorithm. So let's see what will it provide us. Okay, so it gives me a question. So it says that in a given algorithm that solves a specific problem of using randomization, the algorithm randomly samples elements from an input set and performs certain operations on these elements. On average, it makes a fixed number of random selections and operations. The algorithm has a success probability of finding the correct solution, and it terminates when it succeeds. So it gives me three information here. So I will stop the video here and I will try to solve the problem. Then I will come back with the solution. Okay, so I am back with the solution here. As you can see, I've given the solution to ChatGPT. Let's check if it's correct or not. Okay, so here, as you can see, we have the answer of the ChatGPT. So in here, it says that my analysis is correct, and when we check out what it wrote as is actually, it's just the same as what I wrote. So I think we can call this a correct answer. So now let's see my approach. So it gave me a problem, actually a question that considers an algorithm that is randomized. So I picked a quicksort algorithm for that because it's the most common quicksort algorithm of all, and I wanted to explain the aspects of the randomized algorithm on quicksort algorithm. So the first question asks me describe the case steps of the algorithm and how randomization is used. So I wrote down the case steps in our algorithm. We are selecting a random pivot number which divides the array into 2 halves. We put elements in it by taking pivot as a reference. We are putting the elements smaller than the pivot to the left side, and we are putting the elements greater than the pivot to the right side. Then we get 2 arrays, which is left and right, which is partitioned according to the pivot number. and we call our function for these two arrays and do the same approach for these two arrays, which is we are calling it recursively. And then we combine the left and right arrays into one sorted array. So this process has a base case where the size of the array is smaller than or equal to 1. So the function goes until the array size becomes 1 or smaller. So this is the answer to the first question it asked me. So in the second question, it asks me to calculate the expected running time of the algorithm in terms of random selections and operation it performs. I wrote here it's not, it's not a detailed answer, but let me show you the details of this answer here. So here, in quicksort algorithm, in order to calculate the running time of an algorithm, we have to calculate the comparison number between elements. So in order to do that, we can see that here we have an expected value. Since we are working with a randomized algorithm, we have to use this expected value property. So here the sum starts from a equals to 1 to n and b equals to a plus 1 to n, and xab, which is the comparison number. And by the rules of expectations, we can just write it inside of the sum formula, because we are actually dependent on this x variable, so we don't need to write this expectation sign out of the sum formula. So the expectation of x, actually the summing of x times p, xab equals to x. So we are just multiplying the probability of a thing that can occur and the probability or the itself. We are just let's just see it here. So what does this mean? So in a quicksort algorithm, we are actually comparing two elements 1 or 0 times. 1 or 0 times. There is nothing more. There is no other probabilities in this case. So here, their x is 1 here. So the comparison number being 1 and its probability here, and 0 times a probability of being 0. So this is of course it's 0. So or expected value goes to 1 times p x a b equals 1. So if we want to compare this, so if the number of comparison between two numbers should be 1, so we have to select two numbers between numbers a and b if we want to compare this, because in the other probabilities, in the other cases, the two numbers a and b cannot be compared if the pivot number is not selected between these two numbers. So we can show this as 2 over b minus a plus 1. So actually our expected value here equals to 2 over b minus a plus 1. So if we brought this 2 over b minus a plus 1 to here, we can get this. So we can just see that, we are just multiplying it. Not multiplying, we're just summing them up. So 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, blah, blah, blah. So it goes until 1 over n minus a plus 1. So we can say that this is smaller than or equal to 1 over 2 plus 1 over 3 plus 1 over 4 plus goes to 1 over n. So we can say that this is log n. So since we have n elements, we can say that the expected running time goes like n times log n. So this is our expected running time of a quicksort algorithm. So let's see the third question. The third question, it asks me to discuss how the success probability of the algorithm affects its expected runtime. So we say that our expected running time is O n log n. But this may not happen because we are expecting this. So since we are working on a probability, there might be other cases. So for example, if the pivot is selected as the minimum value or maximum value in an array, this means that let's say we are working with a minimum value of the array. So what happens when we select the minimum value? So this means that our left array is going to be empty because all of the values are greater than the element, the pivot. So or the size of the left array will be 0. So this is wrong. This makes our algorithm works more slower, and our running time will jump to O n squared rather than O n log n, which is actually the worst case of our algorithm. So this is basically how I approach to this problem. So let me show you quicksort algorithm. How does it work here? As you can see, so we're importing random firstly, then we have a quicksort algorithm which has it takes a parameter of ARR, which is the array actually. So in the first case, we are checking if the size of the array is smaller than or equal to 1, because if it is, we don't need to apply our function, we just simply return the array to the user. So then we are, by using the random module of the Python, we are creating a random number between 0 and the last element of the array, which is, as you can see, in the index of. So we are just creating a random index here actually in the array. Then we are assigning our pivot value to this array at the index of I, which is randomly selected. Then our left array is selected by the numbers which is smaller than pivot value. As you can see, x or x in array if x is smaller than pivot value. So it creates the left array by checking if the x is smaller than pivot value. And we have a pivot here. I wrote, this is not actually an array, it's just actually the pivot value, but in order to concatenate the lists here, I wanted to show this as a list, just only the pivot value here. And the right array consists of the elements which is greater than pivot value. Then we are concatenating these three, we are partitioning them. We partition them into the left and right arrays. Then we are concatenating them into one sorted array, as you can see. By the way, we are calling this recursively on here, quicksort left, quicksort right, and then we return the sorted array. So let's see if this algorithm works correctly or not. So here, as you can see, I give this 3, 5, 6, 1, 2, 9, 14, 56, and 12. Let's run it again. So as you can see, it works correctly. So let's run it again if it's, there is some problems in it, but I think there is no problems. So we can change this value to 0, for example, and let's see how it behaves. So it's still true, as you can see. If I run it again, so it's true. So this is basically all about my homework for